Today I'll be covering Introduction to Integers. As you are familiar with are whole numbers, which are 0, 1, 2, 3, 4 on the number line. If we extend the number line out to the left, though, to include negative numbers such as -1, -2, -3, and -4, and so on, this whole list of numbers are called integers. And we have, now let's just move on to example 1. Graph 0, 8, and -3. In order to graph an integer, make sure to only use a solid dot because we don't want to include decimals or fractions. So to graph 0, I'm just going to put a solid dot where 0 is. To graph 8, I'm going to put a solid dot where 8 is. And to graph -3, put a solid dot where -3 is. Now let's talk about 6 and -6, which are here and here. If you notice, they're the same number, just opposite signs. And if you count their distance from 0, it's exactly the same. Now my picture might not be the best drawing, but these are supposed to be the exact same distances. And when numbers are on opposite sides of the 0 in the same distance, these numbers are called opposites. So we can think of this negative sign as the word opposite. And now if we go on to something like negative x, what does that really mean? Well, this negative means the opposite of x, so that's -x. But if we take the opposite of an opposite, we end up right back where we were, don't we? So negative x, or negative any number, is just that number. So for example 2, I want you to find the opposites. Well, 0 can either be positive or negative. So really its opposite is 0. Now also keep in mind, these opposites are also called additive inverses because when you add them together, they equal 0. Well, 0 plus 0 equals 0. Now the opposite of -10 will be +10. The opposite of 81 is -81. When we start talking about integers, we can start talking about absolute value also. Because, as I said, with opposites, they were the same distance, correct? Well, because of that word distance, that brings in absolute value, which by definition is the distance from any number to 0. And it is represented by 2 solid bars surrounding a number. So to start off, let's find the absolute value of 9. What I do is I start off at 0 and work my way to the number. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe you didn't need to count that out because you know the distance from 9 to 0 is 9. But now let's do the absolute value of -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Also, what this means is that an absolute value is never negative because a distance can't be negative. So when you take the absolute value of a negative number, it just becomes its positive counterpart. So now let's go on to example 4, which is simplify some expressions. A, -10. What that means is take the opposite of -10, which is 10. Now this gets a little tricky because a lot of people want to say, oh, the opposite of -21. That is not what this is saying, unlike part A. This says the opposite of the absolute value of -21. Because absolute values are just another grouping symbol, we have to evaluate them before anything else, just like parentheses when you do PEMDAS, or please excuse my dear Aunt Sally. So the first thing you have to do is the absolute value of negative 21, which is 21. And then we can evaluate this negative on the outside. And our final answer, because the opposite of 21, is negative 21. Now part C, just the absolute value of negative 7, which is positive 7. Now example 5 is an evaluate problem. Evaluate negative absolute value of negative x if x equals negative 4. That's a lot of negatives. First thing I do is just substitute the negative 4 in for x. These are parentheses, not absolute value bars. I'm trying to make them curved. So if I'm following order of operations, I have to go to my innermost grouping symbol, which are these parentheses. Now this right here says opposite of negative 4, because these are parentheses, not absolute values. Well, the opposite of negative 4 is 4. Now I have to evaluate the absolute value of 4, which is just 4. And the opposite of 4 is negative 4. So the final answer is negative 4. Now we're going to start graphing some inequalities on the number line. For A, x greater than 3. X does not equal 3, but it's every number greater than 3. Since we are dealing with only integers, we do not include decimals or fractions. So I list them by the solid dots. Well, 4 is greater than 3. 5 is greater than 3. And 6, 7, 8, 9, all the way to infinity is greater than 3. To represent that, I'm going to have 3 solid dots above the arrow going to the left. Now, when we do absolute value inequalities and graph them, it's slightly different, because the negatives now become positive when we do an absolute value, correct? So let's find all integers whose absolute value is less than or equal to 2. I always start out at 0. Is 0, the absolute value of 0, is 0. Is 0 less than 2? Yes. 1. Is the absolute value of 1 less than 2? Yes. Absolute value of 2 is 2. Is 2 less than or equal to 2? Well, yes, because it's equal to 2. 3. The absolute value of 3 is 3. Is 3 less than or equal to 2? No. So I stop in that direction because I know the numbers will just get larger. Now, negative 1. The absolute value of negative 1 is 1. Is 1 less than 2? Yes. Absolute value of negative 2 is 2. Is 2 less than or equal to 2? Yes. And negative 3. The absolute value of negative 3 is 3. Is 3 less than or equal to 2? No. And as I go farther and farther away from 0, my absolute value gets larger, so I know I can be done there. And there's my final answer. Now, my last sentence I just said is another way to think about these problems. Is the distance from 0 is less than or equal to 2. So as soon as you get farther than 2, you can stop. I hope you found this helpful, and have a nice day.